Hi, in this second part, we're going to continue with examples for section 4.1. So first, we have to prove following a existential statement and find specific examples that match for those. So the first question is there integers so that a plus b is equal 0? Integers a and b so that a plus b equals 0 with a different from 0. The answer is yes, there's plenty of them. Given that a belongs to the integers, you can always think of b as minus a. That's going to be an integer as well. And notice that a plus that b is going to be 0. A particular example that's going to work for our existence will be a equals 5 and b equals minus 5. If you add those two, then you're going to have 5 plus minus 5, and that's going to be 0. Now, do we have integers such that m times n equals 0, but m different from 0? Sure. The only condition that we have here is that m is different from 0, not that n is different from 0. So we can try, let's say, m. Let's say m equals 3. And we're going to go with n equals 0. So if we have 3 times 0, that's 0. And this works. There's an integer m that makes this work. There is an even prime number. Well, the number 2 is even. So n equals 2 is even. And it's also prime. So that's going to be the example. This is actually the only example that is going to work as even prime number. Now, question number 10. Let's prove for all integers a, b, that if a is even and b is even, then a plus b is even. So this is the same type of proof that we were doing before. Let's consider a and b integers and even. So this is step number 1. This is our assumptions. Step number 2 is going to be the definition of our assumptions. And that means that a is to k and that b is to l for k and l that are integers. Now, if we do the sum, a plus b, then we're going to have 2k plus 2l. And I can factor this as 2k plus l. Now, I'm going to call r equals k plus l. And since k and l belongs to the integers, because the integers are close, k plus l is an integer, so r is an integer. And I can see this as 2r. Notice that this step is step 3, the manipulation. And this final part, the 2r here, is our step 4, which is the definition of the conclusion. So we can say that a plus b is equals to r, and that is going to help us conclude our step number 5, and is that a plus b is even. Now, for question 11, says for all integers n, 3n plus 2 and 5n plus 3 have opposite parity. Now, we gotta check if n is even or odd first for separately. So this is gonna be one case. So case number 1, n is even. So if n is even, n is equals to k, right? For certain k that belongs to the integers. And 3n plus 2 is just going to be 3 times 2k plus 2. And I can just rewrite this pretty much as I can factor out, say, 2. And this will be 3k plus 1. Now, this means because k is an integer, 3k plus 1 is going to be an integer. And so L is an integer. And so this means that this is even. 3n plus 2 is even. Okay? Now, let's take a look at what happens if we do 5n plus 3. 5n plus 3 is 5 times 2k plus 3. But I can just write this as 2 plus 1. So this is 5 2k plus 2 plus 1. And I'm simply going to factor 2. And if I factor 2, I get 5k plus 1 plus 1. Now I'm going to call s equals 5k plus 1. Once again, this is going to belong to the integers. Since k is an integer, 5k is an integer, and hence 5k plus 1 is an integer. So this becomes something of the form 2s plus 1, and so it's odd. So once again, notice that they have opposite parity. Okay. Now, case number 2 will be considering what happens if instead n is odd. So case number 2, n is odd. So if n is odd, I can see n as a 2k plus 1 for certain k that belongs to the integers. And so let's take a look at 3n plus 2. 3n plus 2 will be 3 2k plus 1 plus 2. And this will be 6k plus 3 plus 2. So this will be 6k plus 5. Or I can just simply see this as 6k plus 4 plus 1. And so factor a 2 here, we get 3k plus 2 plus 1. And I can see this as, notice that because k is an integer, this is 3k plus 2 is going to be an integer. And can call this as 2m plus 1. And so this is going to be an odd number. Now, if I take a look at what happened with 5m plus 3, 5m plus 3 is going to be 5 times 2k plus 1 plus 3. And so this is going to be 10k plus 5 plus 3, or 10k plus 8. And I can just factor a 2 here. And I'm going to get 5k plus 4. And so I can consider this because k is an integer, 5k is an integer, 5k plus 4 is an integer. And so I can see this as from the form 2c, where c is an integer. And so this is going to be even. So as you can see, 3m plus 2 is odd and 5m plus 3 is even. So I actually prove question 11 with this. Now, question number 12. Let's check if the following statement is true or false. If true, prove it. If it's false, give you a counterexample. Now, for all integers, if n squared is even, then it's even. And this is something that is going to be a brief example of a type of proof that we're going to see later. And is that if P implies Q, this type of is equivalent to not Q implies not P. So I can instead prove this. This is what is called the contrapositive, and then use it to prove this by the equivalence. So this is equivalent to proving that if n is odd, then n squared is odd. And we actually proved this in the previous video. We essentially remember if n is equals to k plus 1, which is, by the way, this is the definition of my assumption. The assumption here will be that n is odd. And so in the manipulation, I'm going to have n squared, which is going to be 2k plus 1 squared. And once again, this is 4k squared plus 4k plus 1, or twice 2k squared plus 2k plus 1. And because k is an integer, I can see this is of the shade to L plus 1, where L that is an integer. So I'm going to find out that n squared is odd. And this is this step here is the definition of the conclusion, and this is the conclusion. Okay? So I got over all the steps. And notice that by contrapositive, the original statement is true. So this will be something that we'll check more on later, proofs by contrapositives. Now, question 13 is, there exists positive integers a, b, c, so that a squared plus b squared is equal to c squared. Notice that because this is an existential statement, I just need a couple of numbers that make this true. I can try with a equals 3, b equals 4, and c equals 5. This is pretty much the Pythagorean theorem. So I know that 3 squared plus 4 squared is just going to be 9 plus 16, which is 25, which is 5 squared. Okay, so this indeed is true. Similarly, the one before was true. Remember, existential statement, you just need to show one example. Now, for question 14, we want to prove if n and n are integers and m times n is even, then n is even or n is even. So this is kind of hard to do this way. And once again, we're going to use the contrapositive. The contrapositive will be if n and n are both odd, and this will be my assumptions, step 1. Then I want to prove that m times n is odd. Okay, so my definition of the assumptions, if both are odd, then I can write m as 2l plus 1 and n 2s plus 1, where l, s are integers, and then I can make the multiplication m times n, and this is 2l plus 1 times 2s plus 1. We already saw this proof a little bit. The only difference is that now we're having this proven by contrapositive. But we actually proved this in the previous video. So this can be just rewritten as this. And you can see that this is going to be an integer because all this combination is an integer. So this is going to be from the shape 2k plus 1. And so you have that the product, this is my manipulation. And so the definition of the conclusion will be, hey, log that m times n is 2k plus 1, with k being an integer. So this is the definition of the conclusion, is going to be odd. And so m times n is odd. That's my conclusion, step 5. Now in 15, we have, we got to be careful. We got to identify an error in a proof. It says the sum of any two odd integers is even. And the proof is L is let m equals 3 and n equals 5, then m plus n is equals 8, which is even. So the problem here, the error is that this is an example. This is not giving me all numbers. This is just one single example, which is not a valid proof. This is a valid argument, but this is not going to prove it. Okay? We already proved this statement before, that the sum of two odd integers is going to be even in class. So just make sure that when you're checking any of these statements, if you have an example, don't use it as a proof. All right, so this is going to be the end of the class note examples for section 4.1.